In this video, we'll look at a special type of improper integral. This is really very important, and I'm just going to make this video just for this so that you may want to probably download this and keep it somewhere or make a note of this. We are asked the values of p for which this integral is convergent. Now recall that we saw that the integral recall that the integral of 1 over x dx from 1 to infinity is divergent. This was our first example. So that means it doesn't converge for p equal to 1. So we assume that p is not equal to 1 since it doesn't converge for this value of p. Now let's evaluate this integral using improper integral to see other values of p for which this will converge or diverge. Well, by definition of improper integral type 1, this can be written as the limit as t tends towards infinity of integral from 1 to t 1 over x to the power of p dx. We can write this, since n is not equal to 1, we can write this as limit as t tends towards infinity integral of this as x tends to negative p. Now since x is not equal to 1, then this is not going to be natural log of x. The integral will be equal to this. That integral will be add 1 to this, so it's going to be x to the power of negative p plus 1 all over negative p plus 1. And then we are evaluating this from 1 to t. So what would that be? Well, it's going to be equal to this. When x is equal to t, I have t to minus p plus 1 all over minus p plus 1. And when x is equal to 1, I get 1. I just get 1 all over minus p plus 1. I can actually combine these together. If I do, I'll get that this will be equal to the limit as t goes towards infinity of t to the minus p plus 1, which is the same thing as 1 minus p minus 1 divided by 1 minus p. Let me just try this way. It doesn't really matter. So now, how do I find this limit? How do I find this limit? Well, I think it's actually even possible, since 1 over p is a constant. I can factor that outside to even write this limit to look a little bit more easier. So I can have 1 over 1 minus p outside, and then limit as t goes towards infinity, and inside the bracket I had t to the power of negative p plus 1 minus 1, and minus 1 is a constant, so my limit becomes even a bit more easier. So I have 1 minus p into limit as t goes towards infinity of t to the power of minus p plus 1. Then if I take the limit of negative 1, I just get negative 1. So now I'm just looking for the limit of this alone. So let's discuss a little bit what that limit will be. Now, if t is a number bigger than 1, if t is a number bigger, or sorry, if p is 1 Well, we say our p is not 1, so it can never be 1. If p is a number bigger than 1, maybe 3, 4, 5, you will see that this number here is going to be less than 0. If p is bigger than 1, then minus p plus 1 is less than 0. I hope that makes sense, because this number is actually bigger. So if that is the case, then it tells me that this number here, what do you have? This number here is actually a number, and my minus 1 over p will be equal to something all over a fraction because of negative value. That's for p to be, if p is that. On the other hand, if maybe or rather, I think it's a little bit easier to visualize this not in terms of negative, because if something is going like below to negative infinity, it's kind of difficult to visualize unless you're writing it down. Maybe let's rewrite this to the form that we can actually make it easier to visualize. Let's imagine that I'm writing this as 1 over 1 minus p into limit as t tends towards infinity. Then instead of this, I want to factor out negative here, so I'll have like t into minus p minus 1. I'm factoring out that negative, then minus 1 here. So with that now being said, that tells me that if my p is maybe bigger than 1, p is bigger than 1, and then p to the power of p minus 1 is greater than 0. P minus 1 is bigger than 0. So what I have here would be like t to the power of negative a positive number. If that positive number is k, so I have like t to the power of minus k, which is the same thing as 1 over t to the power of k, where this k is a positive number. So as t tends towards infinity, this number here tends towards 1 over infinity, which is 0. So that tells me that as my t tends towards infinity, then my t to the power of minus 1 or minus into p minus 1 tends towards 0. That's 1. Now, assuming my p is less than 1, that's a second case now. If my p is less than 1, then what do I have? Well, this tends to 0, not infinity. If my p is less than 1, that means my p is a p minus 1, let me write it here, should be less than 0, because this guy is less than 1. So if it's less than 0, that means my p will be some p minus 1 is going to be minus k for some positive number k. Now, minus, this whole thing is negative. If I multiply that with negative outside, I get a positive number. I get plus k. Instead of minus minus, I just get a plus. That tells me that if, or as t tends towards infinity, I have that my t to the power of negative p minus 1, which is t to the power of a positive number, would actually tend towards infinity. So that means if my p is less than 1, then this guy is actually less than infinity. So what does it tell us? Well, the limit of this exists when my p is bigger than 1. But if p is less than 1, the limit does not exist. So therefore, in conclusion, the integral, I don't really want, okay, maybe limit of this, I'm running out of space, so I don't know where to put this. I do not know where to put this. Limit as t goes towards infinity of, let me write 1 over p, 1 minus p, into t minus p minus 1 minus 1 is the same thing as 1 over 1 minus p multiplied by, this one here will give me 0, minus 1 if my p is bigger than 1. If my p is bigger than 1, then this is 0. If p is not bigger than 1, this limit does not exist. And this is the same thing as negative 1 over 1 minus p, or you can write it as p 1 over p minus 1. So this thing here converges. In conclusion, the integral from 1 to infinity 1 over, what was that, x to the power of p dx converges to 1 over p minus 1 if p is bigger than 1, and diverges, that means the limit does not exist, if p is less than 1. In fact, when p is equal to 1, the integral diverges also, so we can say that it diverges if p is less than or equal to 1. So you need to kind of, this information here is really very important, that the integral of this exists only when p is bigger than 1. If p is less than or equal to 1, the limit or this integral does not converge. I think I took more time here than I wanted, but it's okay. I hope what I said here is clear enough. And I'll be stopping this video at this point and see how we can apply this concept maybe later on before the end of this section.